And so those are there for you to see. Other things, let's see. Final exam is on Tuesday night next week. That's the next class meeting. There's no recitations. If you have a recitation today, that's the last recitation. There's no recitations next week. There's not regular office hours next week. It's the review sessions, which I'm still waiting to hear back on exactly what room we're going to be in, but there is a final exam review session going to be on Monday 9 to 12, and then Tuesday in the afternoon, and maybe some Monday in the afternoon also, but we're waiting on all the rooms. They're kind of overloaded at the assigning rooms for these sorts of things department. But yeah, there aren't regular classes, so there aren't regular office hours and that sort of thing. Everybody's got final exams to do, including you. So, in any case, just for today, very quiet in here, like the ventilation shut off. For today, just a few kind of wrap-up items that we can do that relate to the fundamental theorem of calculus, overall kind of relationships that tell us all about how things are related, rates and accumulations are related in calculus. So a couple kind of end of the semester wrap-up details with that, including these two I posted in your assignments while you were sitting here taking tests on Wednesday. But these two expressions, and there's one more that's a little bit trickier version of this that I want to talk about also, involve things that if you looked at the iMath AS homework, those last couple assignments that are due next week, Monday night, there are a couple questions that have things like this in them where we've got an accumulation and then a rate of change of that accumulation. So it's kind of like a squaring something and taking a square root. Sometimes you get back what you started with, sometimes you get something slightly different. Like if you square a negative and then take a square root of it, you can get a perfectly good answer. But if you did that in the other order, not quite the same, doesn't work out so well. So taking a derivative and finding an accumulation, depending on all the details, both the function involved and in this case you can see there's where we're measuring the accumulation, is going to have an impact on our answer. So just terminology-wise, we talk about taking derivatives a lot, but that's finding rates of change. With integrals, we talk about integrals. We can talk about finding accumulation. Sometimes also integrals are referred to, and I might have said this word a few times, but I just wanted to point it out. Using integrals with rate functions, we also call that finding antiderivatives, since it's kind of the reverse process of finding a derivative. Sometimes you'll see the phrase antiderivative in terms of measuring this accumulation or finding an accumulation function. So in this first example here, let me get this thing turned on. All right, in this first example here, notice we're finding a rate of change of this weird sine of a cosine of something, weird function here. But if this is a rate of change of something, just thinking your way through this, then this integral sign in front of it along with the dx. So I've got a rate multiplied by a small change in the independent variable. So this is like our mdx expression. And we measure the accumulation from 4 to 7. And then we find the rate of change of that. So I will say that the answer to, like, what does this first thing simplify to? It simplifies down very nicely to, I don't know, one of my favorite numbers. But thinking about this, get this pen on. So if I look at this, like I have no idea how to find an antiderivative for that function. But let's say I did. Let's say that I knew what it was, and I'll call it f of x, since it's got x's in it here. So if I were to able to find the antiderivative of this, and it's f of x. Let me call this, maybe this is f prime of x, so that when I find an accumulation function associated with it, I can say, oh, that's f without the prime of x. And then if that's the antiderivative, I don't actually want an accumulation function based on what this is. I want to know how much accumulates between 4 and 7. Now, regardless of what this mystery, antiderivation, antiderivative. Let me write something that's kind of English here. Antiderivative, there we go. So if f of x without the prime mark is then the antiderivative of this expression there. So whatever f of x, I don't really know. If I want to know the accumulation between 4 and 7, whatever that number might be, it is certainly a number. Would you agree? It's not a formula. The accumulation due to something or another between 4 and 7 is some sort of number. So whether it's a nice simple expression like, oh, maybe I want to figure out what happens to 2x with respect to x, as I let x vary from 4 to 7, say, oh, well, this antiderivative could be anything like x squared, or x squared plus anything I want, but I can pick the simplest, just all variable, varying antiderivative that I want, meaning x squared is something that has 2x as its rate function. And then I evaluate this at 7 and 4. Now, notation for evaluating at 2 points instead of just a subscript, I'm going to evaluate at 7 and 4, because if I don't have a name for this, it's kind of hard to write out, but if I called this f prime and then this is f, then I could say what I want to do is f of 7 minus f of 4, right? Final minus initial. So 49 minus 16, and whatever that is, 33, right? And so if it was this expression here, and I said evaluate that, that's 33. Now if I ask you to take the derivative of that, that's asking you to take the derivative of 33. So what's the derivative of 33? 0. Same thing here. Whatever on earth this function's antiderivative might look like, whatever things it might have to have in it so that I can take a derivative of it and end up looking like that. If I substitute into that 7 and 4, final and initial, and find the change in that accumulation function, then I found a numerical value of some sort. And the derivative of a numerical value, the derivative of constant, is 0. So this is a simpler one to see because we can actually work through what is this mystery antiderivative, or what sort of accumulation function would have that sine of 3 cosine of x as its derivative. I don't know. Let me just say that it's some function called f. Well, if I could find that function called f, I would substitute in independent values of 7 and 4 and subtract to find that net change between 7 and 4. And then I take the derivative. Just order of operations wise, I've got one more step to do. So whatever that number might be, and I don't even know the numerical value, GC could tell me the numerical value, but if I have to take the derivative of it, I know it's going to be 0 even without GC's help. Because if I'm taking the derivative of a constant, the rate of change of a constant, my result's going to be 0. So the next one we're not quite as lucky with. But the thing is, it isn't actually that much more difficult because I need to take the derivative of some mystery function that I don't know. But the thing is, I know that mystery function's derivative. So it should end up being not too hard. Let me clear off this stuff related to the previous problem. All right, so let me do the same sort of trick. In this, I would like to be able to find an antiderivative of this, meaning find a function whose rate of change is this sine of 3 cosine of t. If I can find that antiderivative function, that accumulation of function associated with this rate of change, I want to know, in general, how much it changes between any value of x and a starting point of 4. So a net change between 4 and x, which will be something involving an x, but I get to take the derivative of it. So again, let's say that I call this expression here f of t, or f prime rather, of t. So that I'm just calling it something, so that notation-wise I have something to call its antiderivative, which I don't really want to have to figure out. So if I call this rate of change f prime of t, I just picked t because he was the letter in it, then to evaluate this, I say, oh, well, if the rate of change is this f prime of t, then the accumulation function associated must be f of t. But then I need to know how much f of t changes between any value of x and a starting point of 4, the net change over that interval. So between x and 4, which this is the shortcut notation for saying, oh, evaluate f rather at x, and evaluate at 4 and find the change over that interval. So at this point, I've done almost all of this. So if I call this inner part f prime of t, then I can integrate it symbolically. I can write an antiderivative expression for it, calling it f of t, and evaluate that at x and 4, and subtract to do that final minus initial, to find the net change over the interval. And then I have to take a derivative with respect to x. Now, it's not 0 this time, but if I need to take the derivative of this expression with respect to x, so in other words, what I need to do is take a derivative of two terms, the first of which is called f of x, the second of which is called f of 4. Well, f of 4 is going to be a number, so when I take the derivative, that's 0. What's the derivative of f of x? Symbolically, f prime of x, right? Well, f prime of t is sine of 3 cosine of t. So what's f prime of x? Well, sine of 3 cosine of x. End of story. Here's our answer. So this kind of seems like we're doing things backwards and forward. Like I said, this process of integrating something and then taking a derivative of it, or finding an antiderivative then a derivative, or finding an accumulation then a rate of change of that accumulation. In a sense, it's kind of like that squaring and square root, those two inverse operations. It's just, there's some details, specifically this 4 to 7 or this 4 to x, that we have to think about how that affects, like where we're doing the accumulation. If this accumulation is only over an interval, then the first step of this is finding a numerical value, and the second step is finding a rate of change of a number, which makes it 0. In the second problem, we're not finding a numerical value. Well, one of them's a number and one is a function whose rate of change we already know because we constructed the notation ourselves. So the second problem is more kind of like undoing the exact same thing that we did. So we took a function, we found its rate of change over a general interval, or its accumulation over a general interval, and then found the rate of change of that accumulation on the same interval, which would obviously be what we'd started with. So there's one slightly trickier version of this that I want to point out, and you'll see a question like this in the last, I believe it is, iMath homework. But it's still kind of undoing and redoing the same sort of operation. So we're going to use the same technique, just give a name to that internal function so you can work with this in terms of notation instead of actually worrying about the precise functions. Like notice we didn't do anything with sine and cosine functions or their derivatives or antiderivatives. We just used a symbol to deal with this. So let's see. Hold on for just a sec. There we go. All right, so where were we? Here we go. So we've looked at this question. We just did that one. Here's the second one. We said that the result for this first question was 0 because this accumulation is a number, and the derivative of a number is 0. Derivative of a constant is 0. In this case, we called this function f prime of t, and so the accumulation we got was f of x minus f of 4. And so by taking a derivative of that with respect to x, the 4 is gone, and we just get f prime of x, which is just a letter change away from being exactly what we started with. So that was with t, and now we're with x. So the remaining question I've got has one more small change that makes it a bit more challenging. But what I'd like you to do is think about the steps that we just did. Specifically, the second one is most similar to this. But what this is, if you can't quite see what, I know exponents are hard to see from a distance, but we're taking a derivative with respect to x of this antiderivative of square root of 1 plus w squared, where the limits of integration, the interval over which we're measuring accumulation, is from -5 through not x, but e to the 4x power. So think about how we can do this starts out just the same as the previous one. So take a couple minutes, name that inner function, name that rate function, and see if you can work from there symbolically and get someplace, or at least to a point where you see where it's a little bit different from last time. Right out what that was. Ooh, sorry about that. Nope, my screen wants to go on. Stop. There we go. All right, so on the third one, you do end up having to do a little bit of derivative rules. As opposed to just writing some things and rewriting them with other letters. But just thinking about what we did in the previous question, I'm going to change colors for us here. All right, so I'm going to do what I did before. So let's call this f prime of, I guess, w. And we're asked to find the accumulation due to rate f prime of w, where we let w vary from -5 to e to the 4x. Okay, well, then that should be measuring this accumulation here, same as before, f of, instead of f prime of, f of e to the 4x minus f of -5. And then we need to take a derivative of that with respect to x. So similar to before, this is just a number. So the derivative of that term, of the two terms we get, is going to be 0. But how do I take a derivative with respect to x of f of e to the 4x? What's one derivative rule that's going to be required here? Chain rule. All right. So chain rule says, let's see, in general, I'm going to call the outer function f, so it looks kind of like this. If I have a function f of g of x, and I want to take the derivative of that with respect to x, the variable that's a part of this inner function, we take the derivative of the outer function, leaving the inner alone, and then times the derivative of that inner function. So g prime of x. So let's see here. We want f prime with the inner part left alone. F prime evaluated at e to the 4x power times the derivative of e to the 4x with respect to x. What's the derivative of e to the 4x with respect to x? Just 4e to the 4x. So only question remaining is, how do I write out this without using the symbol f, because that literally was not in the problem. I made that up. You made that up probably too. Well, it's like last time. F prime of t, we were able to convert it to f prime of x by just swapping out the t for an x. F prime of w is square root of 1 plus w squared. F prime of e to the 4x should be the square root of 1 plus e to the 4x quantity squared, which you could simplify that if you felt like it, but we don't need to. And then times 4e to the 4x. So this is just the expression we defined to be f prime, that rate of change function, was originally f prime of w. Now we have f prime of something else. It's just an independent variable or input exchange. We exchanged a w for an e to the 4x. So as I said, this is kind of one of those weird things you can do using our concepts about how derivatives work, about what integration means and accumulation means, and using function notation to help us along the way, because we don't actually, in order to do these problems, need to know what function has a rate of change that looks like this. You could try to come up with one. It's not going to be easy. Like, what could I take a derivative of that ends up like this? Don't know, because things that have a something squared usually have a chain rule involved in their derivative, and I don't see any other stray w's here. So we'll just leave it at that, and we'll use symbols instead. Writing out things symbolically can help you work through lots of types of problems. You can realize how you can simplify or combine terms and not actually have to work out quite as many things as you needed to, or in this case, we don't even have to work out that antiderivative at all. So the other example that I gave you with the 2x, that's the only one where we actually needed to find an antiderivative. So this is probably actually the harder problem on this page. But just thinking about things where we do have to find antiderivatives, if we're not integrating and differentiating, if we're not doing these two opposite sort of operations or inverse type operations, you will generally have to find a function whose derivative is what you see. But if you see something like, oh, let's say like sine of x minus 4, let's see, secant of x, tangent of x. That looks messy, but if you think, well, what sort of function would have these two terms in its derivative? Well, terms can come about one at a time. What sort of function rule would have sine of x as its derivative, as its rate of change? Yeah, a negative cosine of x. So negative cosine of x would have a derivative, or rate of change, that's positive sine of x. What about, let's see, minus 4 secant x tangent x? That secant tangent, when does that come up? As a derivative of what function? Secant. Yeah, so, well, secant of x, derivative would be secant x tangent x, like this. So I'm just going to have to coefficient of, well, negative 4, or, you know, plus a negative 4 or minus 4 secant of x. Now, if it is this, again, just to repeat something we talked about last class, this what's called indefinite integral, what it's really asking for is, what is the family of functions like that has this? So we usually use this kind of generic notation to indicate anything of this sort, this plus c, this constant of integration, anything of this sort would have the same derivative if I throw a constant on the end. Or would have this expression as its derivative. typically what this means, you're not actually doing a whole problem, you're just doing a math exercise like, can you figure out what has this as a rate of change? Because in reality, you're not just figuring out that you wanted to find that accumulation for some purpose, whether it's to construct a new function that varies, from a specific starting point, an accumulation measured from a specific starting point toward x, or if you wanted to know something like, so what if this was the rate of change of a population, what would the population be in 2017? With some numbers to use of some sort, whether numbers as limits of integration, numbers as the beginning and end of accumulation, or one or the other of those. So these just generic problems with an integration symbol and no numbers or symbols on it to indicate where to start and stop are just kind of generic. They're kind of like half a problem. So this isn't like the most important concept on Earth to this plus C part. It's just kind of a placeholder for, and if you want to do something else, realize that depending on what else you're actually going to do with this function, there might be a number as a constant involved here to match up with further details that you have yet to be given. All right, so let's talk about one other sort of random thing that we can do with integration. So this question that kept trying to pop up while I was trying to get just the third problem to show, if you remember when we were talking about initially, before test 2, chapter 5 stuff, talking about having an exact rate of change function and coming up with an approximate rate of change, like step function. I drew this a little bit differently from usual. But having this step function where we use constant rates of change for small intervals. Each interval has its own rate, which when we multiply that by the width of the interval, the delta x or delta t or whatever we're calling the independent variable, we get a small amount of accumulation, which in this graph over here can be shown two ways. You can actually see it as it happens when x goes from 1 to 1 plus a little bit. We follow a straight line path going upward for a little bit, meaning make it match the height there. According to our rate over the width of that first interval, the y value increases at this one constant rate, which contributes to eventually the height by the end of this longer interval composed of lots of subintervals. So if we do this repeatedly and have very small intervals, you can't really see necessarily that the accumulation is being put together a chunk at a time with straight line segments. But something weird that comes up, and it just has to do with x, y coordinates and perpendicular lines, the way we have this set up. In reality, this approximate, like the height generated over here, can also be measured by, if you want to, think of the area that's contributed here. So if I use this rate, this one constant rate for a little bit, because what we were doing to measure accumulation was the rate times delta x. In the rate graph, if you wanted to put it there, which doesn't necessarily make any sense, but you can, so you can like physically draw something there. We have a rate, which is a height, times a delta x, which is a width, and a height times a width, that sounds like an area of a rectangle. You can physically draw rectangles for each of these intervals, and the areas of these rectangles here represent the first rate times delta x, the second rate times delta x, the third rate times delta x, and so on. Whether whether we place them under the curve like this, or with the left edge or the right edge touching is kind of irrelevant. It's all that sort of, we're going to make really small intervals anyway. But in this graph, I can see by drawing these sort of rectangle shapes and calculating their area, the area of these three rectangles added together is the same as if I added together the heights here generated by the first three intervals in this accumulation as an estimate. So it's not really a magical like, oh yay, now we figured out the meaning of life. Like there's rectangles and there's integrals. It's just kind of, maybe kind of interesting. It does have a few applications to things like CAD, sort of like drawing of shapes. You can find areas of things that aren't geometric figures, such as like circles or rectangles or cone. You can find areas of things like that, or volumes of three-dimensional figures, by extending this into a third dimension, by performing integrals, because you can use it to measure physical properties. But this isn't something that we need to do all the time. Usually we've used these integrations not to measure rates of change of the height of a line, but as rate of change of like something else, like a car going down the road or like cement being poured onto like a platform and the weight. But in any case, I just wanted to point out that this integration can also be used to compute area if that's something that you want to compute. So, for instance, oh, and by the way, if you make smaller intervals, you get a better estimate of area. Just like if you do smaller intervals of these constant rates, you get better estimates of the accumulation of anything else. So, picture-wise, if I think of f as a rate of change function, then, let me clear off my dots there, there we go. Then this integral of f of t dt from a to x can represent a net accumulation of something, like whether it's the net accumulation of weight of cement on a scale, the accumulated height of a rocket as it goes up by integrating velocity, or any sort of application that we dealt with in previous homework assignments, and many, many others. If I think of f as instead maybe just the physical shape here, so if I'm interested in this shape, maybe this shape models the boundary of some sort of product I'm trying to fabricate, and I want to know, like whatever shape of plastic this is. I want to make a piece of plastic of that shape. What's the surface area of it? Probably have a little thickness, so I don't just want to say area. But what would be the area of that face of this if this was something in plastic? Well, I can integrate the curve that forms the boundary in order to find that area that accumulates between wherever we start and stop, the vertical lines that form the left and right boundaries of this area. So if you do want to use this to represent something physical, like finding an amount of area bounded by some curve for like a physical production process, that's another kind of random thing that we can do with this because of our rectangular coordinate system. If we're working in other coordinates, which you'll get a chance to do some of that in calculus too, well, it'd be slightly more complex than just integrating, because if you're working with polar coordinates, you don't find areas of circles or parts of circles by doing length times width. It involves pi r squared and stuff like that, angles. But the same principle will hold. If you want to find areas of things generated by curves, you can use integration to help with that using the boundary curve and area formulas, which in the case of rectangles and rectangular coordinates is just length times width. So it's just strictly representing the width of each interval and the height, if you want to think of it that way, the length, that forms each of these, if you can imagine, just kind of extremely tall, narrow rectangles. Not extremely tall, but extremely narrow, and however tall they're going to be represented by the height f of t. So if I then wanted to, there we go, just as an example of finding some area, if I wanted to integrate, here g of x is this blue curve here, if I integrate g of x from negative 0.5 to positive 4, I just wanted to point out one thing about this. So think about this function g of x in terms of if this was a rate function. At some points in time the rate is positive, and at some points in time the rate is negative. Meaning if this was I don't know, temperature would be decreasing for the first while, or temperature would be increasing for the first while until at this point in time I've got negative rates. Rate of change of my temperature is decreasing throughout, decreasing most quickly around time 1.5, and then the temperature starts increasing again at the end when I've got positive rates. The same happens with these areas. So in terms of area, it seems like a simple enough concept, but the picture I had before was all the function we were integrating was above the x-axis, meaning all positive numbers for the heights. In this case, we do have positives and negatives, and those have a meaning. If I were to integrate g of x from negative 0.5 to 4, what that would be finding for me is maybe not what you'd expect. Because this g of x, the boundary curve here, has positive y values, thinking about areas, height times width, I'd get positive areas. So the parts that are colored red there, if I just did those on their own, I'd get a positive area between negative 0.5 and about positive 0.1. And then I get a positive amount of area over here because, again, all my y values, just as if this was rate of change of something else. This looks kind of like the graph, actually, of from test 2, if you remember. There's a toy car that was going forwards and backwards. So this is when the car is going forward, and in the middle it's going back toward you. So if I were to integrate from negative 0.5 through 4, this would give me, in the terms of the toy car, this would give me the net change in position, not how far it traveled. The net change in position of that toy car between those starting and ending points, and it went forward, backward, forward. So, you know, it went back and forth, or this part in the middle canceled out some of the positive progress it had made in terms of going farther away from the person with the toy car. If I actually wanted to know not a net amount of change or a net area, which is what this would give. Net area sounds a little bit weird. Again, this idea of area is useful when you want to find it, but you have to contemplate that this process is really meant to calculate net change. And so when I have positive and negative rates, like we do here that we're integrating, or positive and negative something that we're integrating, if you think of it as rates, we can see that, oh yeah, there's positive progress made in the red colored sections, and during the blue colored section, during that time interval from about 0.1 to 2.8, whatever was happening in the other points in time was being undone, so deaccumulating. So if this is area, if I integrate this, I'm actually going to end up with something, in this case, probably slightly negative, because I can see I accumulate a small bit of positive area here, and at the end another small bit, but those two positive amounts of area are not quite as large as this negative area, if you want to think of that. Because if you think about, if I were calculating height times width one at a time, my heights would all be given by negative y values. So all that area would be being taken away from the positive area that accumulated at the beginning, and then that will reaccumulate at the end. So this actually would come out to be something slightly negative. We can put it in GC to find that, and it makes more sense maybe as a negative in terms of other contexts rather than area, but realize that when you write an integral, the integral and math doesn't know what you mean by this. It doesn't mean, oh, you wanted to find area, you didn't want to find net change, I'm going to come out to be a different answer. That's not how it works. If you wanted to actually calculate these three areas as if they're just all amounts of space, we really want kind of like you can think of it like absolute value of that expression, because I want just the amount of space. I don't care whether it's above or below the axis. But absolute values thrown into integrals make for a big mess. Instead, what we could do is imagine, to find the total area, think about over this first interval, I'll actually integrate g of x. I'm going to do three separate integrals, one for this first section up to x1. And let me change this to a different color. There we go. If I integrate from negative 5 through this point here, it looks like it's about 0.1, or negative 0.5 rather, up through x1. If I integrate g of x there, that will be something positive. Oops, dx. That'll be some sort of positive number. Looks kind of like an area of a triangle. If I wanted to estimate it, I could do it physically that way. If I want to get this area here but have it come out to be a positive, I can integrate from x1 to x2, and I know it'll all come out negative. So none of this will be subtracting from anything else. It'll just be all, not x squared, x1 to x2. And these are values. These aren't like double using x's here. This would come out to be something negative. So if I throw a negative in front of it, now it's positive. Then this third section over here, I could integrate from x2 to whatever this is, 4. Integrate g of x dx. And then I can add these three parts together. So this first section would come out positive all on its own, just integrating from left to right, using this boundary curve, which has all positive y values, positive dependent variable values. So with the third part, so integrating this one from negative 0.5 to x1, this mystery point, and integrating this section from x2 through the right boundary, x equals 4, those would both give me positive values all on their own. If I want to make the center section come out positive, as long as I isolate that part and do it on its own, I can just multiply by a -1 and add it on to everything else. Or in other words, subtract it from the rest of everything else. So, more neatly written, what we need to do is, let me scooch this a little bit, maybe. Can't move it. There we go. Integrate the first section, subtract the integral of the second section, or add the opposite of the second section's integral, and then add on the third section. So when you want to find areas of things, just keep in mind, integrals are meant to measure accumulation. If you want physical area that always comes out positive, if that's what you want, as opposed to wanting accumulation where things can cancel one another out, like going forward versus backward, changes your net position, or temperature increasing versus decreasing, how much net change was there in the temperature. If you want something that's physical area, you might have to separate this out into sections where the accumulation is happening at a positive rate versus a negative rate, so that we don't have positive area and negative area canceling one another out, because net area doesn't really have a normal sort of meaning to it. Total area, adding the three areas together, that sounds like a sort of normal result. So if I want to know how much like metal it would take to cover these three regions, I would integrate g of x over those three sections. And I need to locate where these x-intercepts are in order to make sure that I'm not having my areas cancel out, not just making up something like, I think that's at about x equals 0.1. Doesn't look like it quite, but we can find out where that value is using GC, using algebra, something like that, although maybe not so easy. This looks like a fourth degree polynomial here. So in any case, as a quick summary, so computers, like GC, as I just mentioned, can do the procedural aspect of math very quickly. So that is not what I need you to do. I don't need you to be able to solve for x1 and x2 in that previous example by hand. GC is very good at doing that. You can have to whatever level of accuracy you want. However, you can't just say, GC, here's a picture, do what I want. You have to tell it what operations need to be done, so you need to understand what the operations of mathematics can do for you. So whether it's finding the areas of that weird shape we had or anything else we've talked about, the whole goal of this course is for you to understand what tools we have, what relationships we have, some new ones, rates of change and accumulation for changing functions, not just constant rates of change, one constant rate all the time. How do we put these together so that we can accomplish new things that are beyond algebra level? And we still need people to do that, because although computers are smart and they learn new things every day, the decision-making process, that's a long way away. And putting together the functions are something we always need, whether it's from the actual end user perspective or the person that programs the computer that tells it to understand what people are wanting it to do mathematically. So you could write a program for probably the old TI calculators even, where you could like prompt people, what area do you want to find, and where are the x-intercepts, and blah, blah, blah. And then you could have it do the integral without them knowing it's an integral. But somebody in the background has to write these sorts of programs to do whatever sort of random computation it is that needs to be done if you want a person at the front end of it to not have to know the math. Somebody has to be there, and that could be you. So this class, I hope that through the course of it, over the last, 16 weeks we've been here, that you have a good sense of these rates of change and accumulation and how they're related, these main fundamental ideas of calculus, that they're all related since the beginning of the semester when we were talking about a flag is lowered at a constant rate of 1.8 meters per second, and you know like what you can do with that, how the dy equals mdx and y initial plus mdx and those sorts of things. All those relationships, those all help us generate all the ideas of calculus. It's not new stuff, it's just a twist on an old theme. So I hope that all of it seems like it kind of goes together. This fundamental theorem of calculus, our net change over intervals related to rates of change at every moment within the interval, and how we can accumulate that, and how we can come up with, using algebra skills, closed form functions for that, as well as writing open form functions, the integrals and just the derivative notation sorts of things. So study well for your final exam. I will see you on Tuesday, if not before. I will be posting information about the location for review sessions, which we have yet to hear about. I will let you know that as soon as possible. Make sure if you have a Friday recitation, you do go to that. It's review today. And please ask if you have questions. Thank you so much. About this